Every giant planet in our solar system follows a pattern: a spinning core, a magnetic field roughly aligned with its spin, seasons that make geometric sense, and internal heat leaking steadily outward. Then there is Uranus. Tipped nearly on its side, it rolls around the sun like a barrel. Its magnetic field points in the wrong direction and does not even pass through the planet's center. Its upper atmosphere has been cooling for decades, and nobody fully understands why. For 40 years we relied on a single 6-hour flyby that now appears to have caught the planet during a freak solar storm. The more closely scientists examine Uranus, the less it resembles any giant planet we thought we understood. This is the strangest world in our solar system. If you want to discover why almost nothing about this planet works the way it should, hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. There is a test you can run on every major planet in our solar system. Take its spin axis, draw a line through it, and compare that line to the plane of its orbit. For Earth, the angle between the two is about 23.5 degrees. That modest lean gives us seasons. Summer happens when your hemisphere tilts toward the sun. Winter arrives when it tilts away. The pattern is familiar, it is orderly, it makes intuitive sense. Now run that same test on every other giant planet. Jupiter barely tilts at all, just 3 degrees off vertical, so its seasons are negligible. Saturn leans at about 27 degrees, close enough to Earth's tilt that its seasonal cycle follows a logic any schoolchild could grasp. Neptune tilts at 28 degrees, again within the same comfortable range. 4 giant worlds, and 3 of them sit upright like spinning tops with only a gentle lean. Then there is Uranus. Uranus does not lean. Uranus lies down. Its axial tilt measures 97.8 degrees, which means the planet is tipped just past horizontal. It does not spin like a top. It rolls through space, like a ball someone kicked along a flat surface. No other major planet comes close to this geometry. The next most tilted giant, Neptune, has a tilt less than 1/3 as extreme. Among all 8 planets, only Venus approaches a comparable tilt, and Venus achieves it through a completely different mechanism. Its rotation is retrograde, effectively flipped upside down rather than knocked sideways. Uranus is not flipped, it is sideways, and that distinction reshapes everything about how the planet works. To understand why this tilt is so disorienting, you need to picture what it does to the planet's relationship with the Sun. On a world tilted at 23 degrees, like Earth, every point on the surface experiences a cycle of longer and shorter days as the planet orbits. Even the poles, which endure months of continuous darkness or continuous daylight, still transition between the two over the course of a year. The geometry is manageable. Light and dark trade off on a rhythm that life can track and adapt to. Combine that enormous orbital period with the sideways tilt, and the result is a seasonal cycle unlike anything else in the solar system. When Uranus reaches the point in its orbit where its north pole aims almost directly at the Sun, that pole receives continuous sunlight. Not for a few months the way Earth's Arctic does. For roughly 42 years. The entire northern hemisphere basks in decades of unbroken daylight, while the southern hemisphere sits in decades of unbroken night. Then the planet crawls around to the opposite side of its orbit, and the arrangement reverses. The south pole faces the Sun. The north pole plunges into darkness. Another 42 years pass before the cycle turns again. Between these extremes, Uranus passes through brief equinox periods where the Sun shines roughly on the equator, and both hemispheres share more equal lighting. But even these transitional periods last only a few Earth years. Thin windows of normalcy sandwiched between decades of polar exposure. The most recent equinox occurred in 2007. Before that, the previous one was in 1965. The next will not arrive until 2049. Entire human careers begin and end between Uranian equinoxes. This is not just an astronomical curiosity. It has real consequences for how the planet behaves. On a normally tilted world, solar energy distributes itself across the globe in a relatively balanced way. The tropics absorb the most energy. The poles absorb the least. Atmospheric circulation patterns develop to move heat from the warm equator toward the cooler poles, creating the trade winds, jet streams, and storm systems we observe on Jupiter, Saturn, and Neptune. Uranus breaks this pattern completely. When one pole points at the Sun, that pole receives more solar energy per unit area than the equator does. The warmest point on the planet is the pole, not the equator. Atmospheric circulation has to work in reverse, or at least in a geometry that no other giant planet demands. Heat must redistribute itself around a world where the energy input comes from the top rather than the middle. You might expect this to produce spectacular weather. A pole baking in sunlight for 4 decades, while the opposite hemisphere freezes, should generate enormous temperature contrasts and violent storms. And yet, when Voyager 2 flew past Uranus in January of 1986, the planet looked almost blank. Its atmosphere appeared as a pale blue-green sphere with virtually no visible cloud features. Compared to the vivid bands of Jupiter or the raging storms of Saturn, Uranus seemed eerily quiet. Scientists at the time described it as the most boring-looking planet in the solar system. That assessment turned out to be spectacularly wrong, but the reasons would take decades to uncover. What matters here is the deeper point. The tilt alone should produce a planet with dramatic, pole-centered weather patterns unlike anything on Jupiter or Saturn. Instead, Uranus appears to suppress its own strangeness, hiding whatever is happening beneath a mask of pale, featureless haze. The planet looks calm when it should look chaotic. That contradiction is the first sign that something fundamental about Uranus does not work the way we expect. The obvious question is how a planet ends up tilted this far. Giant planets form from the same rotating disk of gas and dust that produces their parent star. Material in that disk orbits in a flat plane, and as it collapses into planets, angular momentum keeps everything spinning in roughly the same direction. Newly formed giant planets should spin nearly upright, with tilts close to zero. Jupiter's tiny 3-degree tilt is exactly what formation models predict. Saturn and Neptune have modest tilts that can be explained by gravitational interactions with other planets over billions of years, gentle nudges accumulated across cosmic time. Uranus cannot be explained by gentle nudges. 97.8 degrees is not a gradual drift. Something violent happened to this planet, and the leading hypothesis is a giant impact. Early in the solar system's history, when the planets were still settling into their orbits and debris was far more abundant, a massive object, something roughly the size of Earth or perhaps larger, may have slammed into the young Uranus at tremendous speed. The energy of that collision would have been sufficient to knock the planet onto its side, reshaping its spin axis in a single catastrophic event. This hypothesis is compelling. It provides a straightforward mechanism for producing such an extreme tilt. Computer simulations of giant impacts can reproduce the 98-degree angle under certain conditions, particularly if the impactor struck at a glancing angle rather than head-on. A glancing blow would transfer angular momentum in a way that tips the planet sideways without completely destroying it. But here is where the story becomes less tidy. The impact hypothesis explains the tilt, but it struggles with the details. One major problem involves the moons. Uranus has 29 known moons, and the 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, all orbit in the planet's equatorial plane. Their orbits are tilted along with Uranus, which means they are also nearly perpendicular to the planet's orbital plane around the Sun. If a giant impact knocked Uranus sideways after the moons had already formed, the moons should still be orbiting in the original plane. They should not have followed the planet's new tilt. The fact that they did follow it suggests one of 2 possibilities. Either the moons formed after the impact, coalescing from a debris disk generated by the collision, or some mechanism dragged the existing moons into the new equatorial plane over time. Both explanations have problems. If the moons formed from impact debris, simulations show that the debris disk tends to produce moons that are too small or too close to the planet to match the actual Uranian system. The 5 major moons orbit at substantial distances and have significant masses. Generating them from a single impact requires very specific conditions that models struggle to reproduce consistently. If instead the moons were dragged into the new plane by tidal forces or disk interactions, the timescales and energy requirements are difficult to reconcile with what we know about the early solar system. Some researchers have proposed an alternative. Instead of one massive impact, Uranus may have experienced 2 or more smaller impacts that cumulatively tilted it to its current angle. Multiple impacts could explain the tilt, while also providing repeated opportunities for debris disks to form and generate moons. This scenario is statistically plausible. The early solar system was a violent place, and multiple collisions with large protoplanets were common, but it introduces additional free parameters that make the hypothesis harder to test. A completely different class of explanations avoids impacts altogether. Some models suggest that gravitational interactions with a now-lost giant planet could have gradually torqued Uranus's spin axis over millions of years. If a massive planet once orbited nearby and was later ejected from the solar system, its gravitational influence during the time it was present could have driven Uranus's tilt to extreme values through a process called spin-orbit resonance. This mechanism can produce large tilts without any collision, but it requires a specific planetary configuration that is difficult to confirm or rule out billions of years after the fact. The honest answer is that we do not know exactly how Uranus ended up on its side. The giant impact hypothesis is the most widely cited explanation, and it remains the leading candidate, but it is not proven. Every model that reproduces the tilt introduces complications that remain unresolved. The tilt is a confirmed observation. The cause is a hypothesis with supporting evidence, but also significant gaps. What makes this uncertainty so important is that scientists initially treated the tilt as the single defining oddity of Uranus, the one thing that needed explaining. Once you explain the tilt, everything else should follow. The extreme seasons are a consequence of the tilt. The weird magnetic field might be a consequence of the tilt. The quiet atmosphere might be a consequence of the tilt. In this framing, Uranus is a normal giant planet that got knocked over, and all its strangeness flows from that single event. That framing is almost certainly too simple. The more data we collect, the more it becomes clear that the tilt is not the sole source of Uranus's strangeness. It is one symptom in a constellation of anomalies, each of which raises its own questions. The seasons are strange, yes, but the atmosphere does not respond to them the way models predict. The magnetic field is strange, but its geometry cannot be explained by the tilt alone. The internal heat is strange in ways that have nothing to do with axial orientation. The moons are strange. The rings are strange. Each system on Uranus seems to follow its own logic, as if the planet were assembled from parts that do not quite belong together. Consider the seasons again. 42 years of continuous polar sunlight should heat the sunlit pole substantially, and measurements confirm that it does. The sunlit pole is slightly warmer than the rest of the planet, but the temperature difference is far smaller than models predict. Uranus seems to distribute heat more efficiently than expected, or its atmosphere responds more sluggishly to solar input, or some internal process moderates the seasonal contrast. When the Hubble Space Telescope and later ground-based observatories monitored Uranus through its 2007 equinox, they observed cloud activity increasing and bright storm features appearing at mid-latitudes. The planet was waking up, but the pattern of activity did not match straightforward seasonal predictions. Some storms appeared in the wrong hemisphere, others intensified years after the equinox had passed, as if the atmosphere were responding on a delay that standard models did not anticipate. Even the colour of Uranus connects to its strangeness. The pale blue-green hue comes from methane in the upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue and green light back into space. Methane is present on Neptune too, but Neptune appears a deeper, more vivid blue. The difference likely relates to the distribution of haze particles in the upper atmosphere. Uranus has a thicker, more uniform haze layer that washes out its colour, giving it that distinctive pale, almost washed-out appearance. Why Uranus produces more upper atmospheric haze than Neptune, a planet of similar size and composition, is another open question. The haze may be connected to photochemistry driven by the unusual solar illumination patterns created by the extreme tilt, or it may relate to differences in atmospheric circulation, or it may involve interior processes that feed different amounts of methane into the upper atmosphere. Layer by layer, the strangeness accumulates. The tilt creates alien seasons. The alien seasons should drive extreme weather, but the weather appears muted. The colour should match Neptune's, but it does not. The moons should orbit in the original plane, but they follow the tilted equator. The impact that explains the tilt should leave predictable signatures, but the details resist clean explanation. And all of this, every feature discussed so far, describes only the outermost, most visible aspects of the planet. The tilt is dramatic, but it is the surface of the mystery. Beneath it lies something far stranger, something that has baffled planetary scientists since Voyager 2 sent back its data 4 decades ago. The magnetic field of Uranus is not just unusual, it is, by every standard used in planetary science, wrong. It points in the wrong direction, it originates from the wrong place inside the planet, and it creates a magnetosphere so contorted that it reshapes itself with every rotation. On Earth, the magnetic field runs roughly from pole to pole, aligned within about 11 degrees of the spin axis. On Jupiter, the alignment is even tighter, about 10 degrees. On Saturn, the magnetic field and the spin axis are almost perfectly aligned, offset by less than 1 degree. These alignments are not coincidental. They reflect the physics of how planetary magnetic fields are generated. Deep inside a planet, electrically conducting fluid liquid metallic hydrogen on Jupiter and Saturn, molten iron on Earth circulates in patterns driven by the planet's rotation. This circulation, called a dynamo, generates a magnetic field that naturally aligns with the spin axis, because the rotation itself organizes the fluid flow. Uranus has a magnetic field, but it follows none of these rules. Its dipole axis is tilted approximately 59 degrees away from the rotation axis. It does not pass through the center of the planet. Instead, it is offset by roughly 1/3 of the planet's radius toward the southern hemisphere. The result is a magnetic field that is dramatically lopsided. At some points on the surface, the field strength is several times greater than at others. The geometry looks less like a bar magnet neatly centered inside the planet, and more like someone jammed a bar magnet in at an odd angle and shoved it off to one side. This matters because the magnetic field creates the magnetosphere, the vast bubble of charged particles and magnetic influence that surrounds a planet and shields it from the solar wind. On Earth, the magnetosphere has a relatively stable shape, compressed on the sunward side and stretched into a long tail on the night side. It shifts and flexes during solar storms, but its overall geometry remains consistent because the magnetic field maintains a steady orientation relative to the solar wind. On Uranus, nothing about the magnetosphere is steady. Every 17 hours, as the planet completes one rotation, the tilted, offset magnetic field swings through space like a wobbling gyroscope. The magnetic poles sweep across entirely different orientations relative to the incoming solar wind. At one point in the rotation, a magnetic pole might face the sun almost directly. A few hours later, the magnetic equator faces the sun instead. The magnetosphere does not simply flex, it reconfigures itself on a cycle shorter than a single Earth day. No other planet in the solar system experiences anything like this constant magnetic churning. The consequences of this churning ripple outward in every direction. The solar wind interacts with the magnetosphere differently at every phase of the rotation. Charged particles get funneled along field lines that change their geometry hour by hour. Auroras, the glowing displays created when charged particles strike the atmosphere, do not sit neatly above the poles the way they do on Earth or Jupiter. On Uranus, auroral emissions sweep across the planet's surface following the offset magnetic poles, painting shifting patterns that the James Webb Space Telescope only recently began to map in 3 dimensions. And the magnetosphere connects downward too. The magnetic field is generated somewhere inside the planet, in a region where the internal material becomes electrically conducting. On Jupiter and Saturn, this region is deep metallic hydrogen crushed under enormous pressure near the core. On Uranus, the conducting region is thought to be a layer of water, ammonia, and methane, compressed into an exotic, electrically conducting fluid, sometimes called a superionic state. This layer sits at intermediate depths, not at the core, which may explain why the magnetic field is offset rather than centered. The dynamo does not operate at the planet's heart. It operates in a shell, a thick band of conducting material wrapped around a deeper interior, whose nature remains almost entirely unknown. Understanding what that shell actually is requires confronting one of the stranger consequences of extreme pressure. At the depths where Uranus's magnetic field is thought to originate, somewhere between roughly 1/4 and 2/3 of the way down from the cloud tops, Pressures reach millions of times the atmospheric pressure at Earth's sea level. At these conditions, the familiar molecules that make up much of the planet's interior, water, ammonia, methane, stop behaving like anything you would recognize. Water does not flow as a liquid or sit as a solid. Instead, the oxygen atoms lock into a rigid crystalline lattice, while the hydrogen atoms detach and move freely through the lattice like electrons through a metal. This state, called superionic water, is simultaneously a solid and a conductor. It carries electrical current not through free electrons, as metals do, but through the movement of hydrogen ions drifting through a frozen scaffold of oxygen. Laboratory experiments using powerful lasers to briefly recreate these conditions have confirmed that superionic water exists and that it conducts electricity well enough to sustain a magnetic dynamo. This is almost certainly part of what generates the field inside Uranus. A layer of superionic water mixed with ammonia and other compressed volatiles, circulating under the combined influence of the planet's rotation and internal heat gradients, drives electrical currents that produce the observed magnetic field. But the key distinction from the gas giants is where this layer sits. On Jupiter, the conducting region extends all the way to the core. Liquid metallic hydrogen fills the deep interior, creating a dynamo that occupies most of the planet's volume and naturally produces a strong, centered, axially aligned field. On Uranus, the conducting layer is a shell bounded above by a non-conducting hydrogen-helium envelope and below by a deeper interior that may or may not conduct electricity, depending on its composition. A shell dynamo does not have the same symmetry as a deep dynamo. The geometry of the conducting region, its thickness, its inner and outer boundaries, how convection patterns circulate within it directly shapes the geometry of the magnetic field it generates. This distinction matters enormously because Neptune has a similar problem. Neptune's magnetic dipole is tilted about 47 degrees from its rotation axis, an offset from the planet's center by roughly half a planetary radius. The numbers differ from Uranus's 59-degree tilt and one-third offset, but the qualitative picture is the same: a strongly tilted, significantly offset magnetic field that cannot be produced by a centered deep dynamo. Two ice giants, both with radically off-axis fields. Two gas giants, Jupiter and Saturn, both with neatly aligned fields. The pattern is too clean to be coincidental. It suggests that the strange magnetic geometry is not a quirk specific to Uranus, not a scar from whatever impact knocked it sideways, but a fundamental characteristic of ice giant interiors. The shell dynamo appears to be the common factor. Both Uranus and Neptune likely generate their fields in intermediate depth conducting layers rather than in deep metallic cores, and shell dynamos inherently produce fields with larger tilt and offset, because the conducting geometry lacks the full spherical depth that forces alignment with the spin axis on gas giants. If this interpretation is correct, then the magnetic weirdness of Uranus is not about Uranus at all. It is about what happens inside any planet whose interior is dominated by compressed ices rather than metallic hydrogen. Every ice giant-sized world in the galaxy, and there appear to be billions of them, may carry a similarly tilted, offset, tumbling magnetic field. The magnetospheres of these worlds would undergo the same constant reconfiguration that Uranus experiences, with consequences for atmospheric chemistry, auroral heating, and the radiation environment that we have barely begun to explore. But we cannot test this hypothesis with models alone. We need to measure the higher-order structure of Uranus's magnetic field, the quadrupole, octopole, and finer components that encode the shape and depth of the dynamo region. Voyager 2 measured the dipole and a rough quadrupole during its 6-hour pass. An orbiter circling the planet for years, sampling the field from many altitudes and latitudes, would map these higher-order terms with the precision needed to distinguish between competing dynamo models. That measurement alone would be worth the mission. This is where the strangeness stops being a collection of individual oddities and starts becoming something more unsettling. The tilt is strange. The seasons are strange. The magnetic field is strange. The magnetosphere is strange. And all of these systems are connected. The tilt influences the seasons. The interior structure shapes the magnetic field controls the magnetosphere, and the magnetosphere determines how the solar wind interacts with the atmosphere. Each system feeds into the next. Each anomaly amplifies the others. But the chain does not stop at the magnetosphere. It reaches deeper into the planet's interior, where another puzzle waits. For decades after Voyager 2, Uranus appeared to be the only giant planet that did not radiate significant excess heat from its interior. Jupiter, Saturn, and Neptune all glow in the infrared, releasing far more energy than they receive from the Sun, powered by leftover heat from their formation and ongoing gravitational contraction. Uranus, by contrast, seemed thermally dead, a giant planet that had somehow lost or locked away its primordial warmth. That mystery, too, has recently begun to shift, and what the new data reveal is not a simple answer. It is another layer of strangeness, another system that does not work the way it should. The interior of Uranus, like everything else about this planet, appears to operate under rules that the other giants do not follow. The magnetic field of Uranus is tilted, offset, and generated in a shell of exotic conducting fluid rather than at the planet's core. Those facts alone make Uranus a magnetic outlier, but stating the geometry only opens the door. What matters is what that geometry does, how it reshapes the space environment around the planet, how it drives energy into the atmosphere, how it confused the only spacecraft that ever visited, and why recent telescope observations have revealed that even our confusion was based on incomplete evidence. Start with what the magnetic field produces when it interacts with the solar wind. Every planet with a magnetic field carves out a cavity in the stream of charged particles flowing outward from the Sun. That cavity, the magnetosphere, is the region where the planet's magnetic influence dominates over the Sun's. On Earth, the magnetosphere extends roughly 65,000 kilometers on the sunward side and stretches millions of kilometers downwind into a long magnetic tail. The shape stays broadly consistent because Earth's magnetic axis is nearly aligned with the spin axis. The field presents a stable face to the solar wind. Reconnection events and solar storms disturb it, but between storms, the system relaxes back to a predictable configuration. Jupiter's magnetosphere is the largest structure in the solar system after the Sun itself. It could contain the Sun with room to spare, yet even this colossus maintains a recognizable shape compressed on the day side, stretched on the night side, organized around a magnetic axis that deviates only about 10 degrees from the spin axis. Saturn's magnetosphere is smaller, but even more orderly, with a magnetic axis so close to the spin axis that the two are nearly indistinguishable. These magnetospheres flex and breathe with the solar wind, but their fundamental architecture remains constant from one rotation to the next. Uranus does not have that luxury. That 59-degree divergence between the magnetic axis and the spin axis is compounded by a further misalignment. Neither axis points toward the incoming solar wind. The spin axis itself points roughly toward the Sun during solstice, a consequence of the 98-degree axial tilt, which means the planet's rotation carries the magnetic poles through wildly different orientations relative to the solar wind over the course of each 17-hour day. At one moment during the rotation, a magnetic pole may face the Sun almost directly, opening the magnetosphere to direct solar wind entry along the polar cusp. A few hours later, the same pole has swung away and the magnetic equator faces the Sun instead, presenting a completely different magnetic geometry to the incoming plasma. The magnetosphere does not just wobble. It undergoes a topological transformation with every rotation, cycling between configurations that on any other planet would require a major solar storm to produce. Think of it this way. On Earth, a severe solar storm can compress the magnetosphere, trigger magnetic reconnection, and temporarily reshape the entire magnetic environment. These events are dramatic, newsworthy, and relatively rare. On Uranus, the magnetic field's own rotation drives an equivalent level of reconfiguration every 17 hours as a matter of routine. The planet lives in a state of perpetual magnetic disruption that Earth experiences only during its most extreme space weather events. This constant reconfiguration has consequences that cascade through the entire Uranian system. Charged particles trapped in radiation belts around the planet experience shifting magnetic field lines that can accelerate them, scatter them into the atmosphere, or eject them into interplanetary space depending on the phase of the rotation. The radiation environment around Uranus is not stable the way Jupiter's intense radiation belts are stable. It fluctuates on timescales of hours, driven by the geometry of the tumbling field rather than by external solar wind variations. The auroral emissions that result from this churning are equally unusual. On Earth, auroras form glowing rings centered on the magnetic poles. On Jupiter, the auroral ovals are among the most energetic phenomena in the solar system, driven by the planet's rapid rotation and its interaction with the volcanic moon Io. In both cases, the auroral zones stay fixed relative to the magnetic poles and maintain a broadly consistent shape over time. On Uranus, the auroral zones cannot stay fixed because the magnetic poles themselves sweep through different orientations with every rotation. The auroras migrate across the planet's disk, appearing and fading in patterns that track the wobbling magnetic geometry rather than sitting in permanent polar caps. For decades, these auroral patterns were essentially invisible. Uranus is so far from the Sun, approximately 19 astronomical units, nearly 3 billion kilometers, that the energy available to drive auroral emissions is far weaker than at Jupiter or Saturn. Ground-based telescopes detected faint hints of auroral activity in the infrared, but the signals were marginal, barely above the noise floor. Ultraviolet detections from the Hubble Space Telescope confirmed that auroras existed but could not resolve their spatial structure in meaningful detail. Scientists knew the auroras were there. They could not see what they were doing. That changed in early 2026, when a team led by Paola Tiranti of Northumbria University published the first three-dimensional map of Uranus's upper ionosphere, constructed from data gathered by the James Webb Space Telescope. On January 19, 2025, the telescope's near-infrared spectrograph observed Uranus continuously for 15 hours, nearly one complete planetary rotation. The instrument tracked emissions from H3+, a molecular ion that forms in the ionospheres of giant planets and radiates in the near-infrared. H3+ quickly reaches thermal equilibrium with the surrounding neutral atmosphere, which means its emission brightness and spectral shape directly reveal the temperature and density of the ionosphere at the altitudes where it exists. What Webb found was striking. The data revealed two bright bands of auroral emission located near the magnetic poles, separated by a lower emission region between them. These bands were not static. They shifted in brightness and position as the planet rotated, tracking the offset magnetic field geometry exactly as models predicted, but observations had never confirmed. The emission profiles showed temperatures between approximately 380 and 480 Kelvin across all longitudes, with a modest temperature enhancement at altitudes between 3,000 and 4,000 kilometers above the cloud tops. The temperature measurements were consistent with earlier ground-based observations, but added an entirely new dimension literally. For the first time, scientists could see how temperature and density varied vertically through the ionosphere, not just as averages across the disk. The vertical profiles revealed something unexpected about how energy moves through Uranus's upper atmosphere. In a purely collisional regime, where energy deposited by auroral particle precipitation gets transferred efficiently to surrounding neutral gas, scientists would expect strong spatial gradients and rapid cooling with altitude. Instead, the Webb data showed weak longitudinal gradients and elevated temperatures persisting to surprisingly high altitudes. This implies that additional heating or energy redistribution processes are at work. Gravity wave dissipation, thermal conduction, or some other mechanism transporting heat more efficiently than particle collisions alone can explain. The magnetic field's offset geometry may play a role here, funneling energy into the atmosphere at unusual angles and distributing it along paths that a centered, aligned field would not produce. The Webb observations also connected to a longer-running mystery. Since the early 1990s, ground-based infrared telescopes have tracked the temperature of Uranus's thermosphere, the tenuous upper atmospheric layer where H3+ resides. When Voyager 2 flew past in 1986, the spacecraft's ultraviolet spectrograph measured a thermospheric temperature of approximately 750 Kelvin. That was already puzzling, because solar heating alone at Uranus's distance from the Sun should produce temperatures far lower, perhaps only a few hundred Kelvin. Something was pumping energy into the upper atmosphere beyond what sunlight could provide. But the real surprise came over the following decades. Ground-based measurements showed that the thermospheric temperature was not holding steady. it was falling. By 1992, the temperature had dropped to roughly 715 Kelvin. By 2008, it had declined to about 534 Kelvin. The cooling continued at a rate of roughly 8 Kelvin per year, a relentless downward trend spanning more than 2 decades. By the time Webb observed the planet in 2025, temperatures had settled around 415 to 450 Kelvin, roughly half the value measured during the Voyager era. The cause of this dramatic cooling is still debated. One hypothesis, proposed by Adam Masters and colleagues in 2024, suggests that the solar wind drives thermospheric heating at Uranus, and the long-term decline in solar wind power reaching the planet's orbit explains the cooling. As the sun's output varies over decades, and as Uranus's changing orbital geometry alters how the solar wind strikes the magnetosphere, the amount of energy funneled into the upper atmosphere through magnetosphere-ionosphere coupling would change accordingly. In this view, the thermosphere acts as a thermometer for solar wind conditions at 19 astronomical units. But this hypothesis ran into trouble almost immediately. Jamie Jasinski and colleagues at NASA's Jet Propulsion Laboratory published a study in late 2025 showing that since approximately 2009, solar wind power at Uranus has actually increased by roughly 34% in dynamic pressure and about 40% in energy flux. If the solar wind were the primary driver, temperatures should have risen or at least stabilized during this period. Instead, they continued falling. The cooling trend persisted even as the solar wind strengthened, which strongly suggests that the solar wind is not the dominant factor. An alternative explanation invokes what some researchers call a magnetic season, a phenomenon unique to Uranus. Because the magnetic pole is separated from the rotational pole by 60 degrees, and because the magnetic dipole is offset from the planet's center, the geometry of how the magnetic field faces the incoming solar wind changes slowly over the course of Uranus's 84-year orbit. This slow geometric shift could modulate the efficiency of magnetosphere-ionosphere coupling, gradually increasing or decreasing the amount of auroral and Joule heating deposited in the upper atmosphere over decades. The cooling observed since the 1980s might represent one phase of this magnetic seasonal cycle, a phase in which the coupling efficiency declines, reducing the energy input to the thermosphere. A further study published in March of 2026 added another piece to the puzzle. Dolon Bhattacharya and colleagues used Hubble Space Telescope far ultraviolet observations spanning 1998 to 2022 to track the behavior of Uranus's exosphere, the outermost, atmospheric layer above the thermosphere. They found that the exosphere has also been cooling, but only since 1998, lagging behind the thermospheric trend. The exospheric cooling manifested as a steady collapse of the hydrogen scale height, meaning the exosphere was contracting as it lost thermal energy. This contraction was not matched by changes in the lower atmosphere below the 1 microbar pressure level, where Spitzer spacecraft infrared observations showed no comparable cooling trend. The picture that emerges is one of an upper atmosphere losing energy from the top down, with the thermosphere cooling first and the exosphere following years later, while the deeper atmosphere remains largely unaffected. Whatever is driving the cooling operates in the region where the magnetic field couples to the atmosphere, not in the bulk interior. The mechanism is almost certainly connected to the unique magnetic geometry, but the exact chain of cause and effect remains unresolved. All of this, the Webb ionosphere maps, the decades-long cooling trend, the competing hypotheses about solar wind and magnetic seasons, underscores a single uncomfortable truth. We have been studying Uranus's upper atmosphere and magnetic environment from 3 billion kilometers away, using instruments that were never designed for this purpose. Ground-based telescopes strain to detect faint infrared emissions from H3+ ions in an atmosphere illuminated by a distant sun. Space telescopes like Hubble and Webb provide extraordinary data, but they observe the planet as a tiny disk, a few pixels across in most instruments, with limited ability to resolve spatial detail below continental scales. The information we have extracted is remarkable given these constraints, but it is also fundamentally incomplete. And the most complete dataset we possess, the Voyager 2 flyby, now appears to have been compromised by timing. When Voyager 2 encountered Uranus on January 24, 1986, It provided humanity's first and so far only close look at the planet. The spacecraft passed within 81,500 kilometers of the cloud tops, discovered 10 new moons and 2 new rings, measured the magnetic field geometry, sampled the radiation environment, and captured images that defined our visual understanding of Uranus for the next 4 decades. The encounter lasted only about 6 hours at close range. Everything we learned had to be extracted from that single brief window. For nearly 40 years, the Voyager 2 data shaped how scientists understood Uranus. The magnetic field measurements revealed the extreme tilt and offset. The particle detectors measured a surprisingly intense electron radiation belt, far stronger than models predicted for a planet at Uranus's distance from the Sun. The plasma instruments found unexpectedly low levels of plasma in the magnetosphere, with a puzzling absence of water group ions near the major moons, ions that should have been present if those moons were geologically active or if their surfaces were being sputtered by magnetospheric particles. The overall impression was of a magnetically bizarre but otherwise quiet system, with radiation belts that were inexplicably energetic and a magnetosphere that seemed strangely depleted. In 2024, Jamie Jasinski's team at the Jet Propulsion Laboratory re-examined the Voyager 2 data with a fresh perspective and reached a startling conclusion. The spacecraft had almost certainly arrived during a rare solar wind compression event, a surge in solar wind pressure, likely a co-rotating interaction region, a structure where fast solar wind overtakes slower wind and creates a pileup of plasma and magnetic field, had struck Uranus's magnetosphere shortly before or during the flyby. This compression event squeezed the magnetosphere to roughly 20% of its normal volume. The implications cascade through every measurement Voyager 2 made. The intense radiation belts that puzzled scientists for decades may not represent normal conditions at all. In December of 2025, Robert Allen and colleagues at the Southwest Research Institute published a study comparing the Voyager 2 radiation belt observations to similar solar wind-driven events measured at Earth. They found that co-rotating interaction regions at Earth can generate powerful high-frequency electromagnetic waves, so-called chorus waves, that rapidly accelerate electrons to relativistic energies, dramatically boosting radiation belt intensity over short timescales. If a similar process occurred at Uranus during the Voyager encounter, it would explain the extreme radiation levels as a transient phenomenon rather than a permanent feature of the Uranian system. The depleted plasma levels and the absence of water group ions near the moons also make more sense under the compression hypothesis. A powerful solar wind event would have driven plasma out of the magnetosphere entirely, temporarily emptying the system of the ions that normally populate it. The missing water ions near the 5 major moons, which had led some scientists to conclude that the moons were geologically inert, may simply reflect a magnetosphere that had been flushed clean by the solar wind hours or days before the spacecraft arrived. The moons might actually be geologically active, producing water vapor or surface material that gets ionized and swept into the magnetosphere under normal conditions. Voyager 2 may have caught the system in a rare depleted state that told us nothing about its typical behavior. Jasinski estimated that the conditions Voyager 2 observed occur only about 4% of the time. If the spacecraft had arrived a few days earlier or later, it would have encountered a completely different magnetosphere, one more representative of the planet's normal state. The magnetic field geometry would have been the same, because that is an intrinsic property of the planet. But the radiation environment, the plasma populations, the particle dynamics, and the moon interactions might all have looked dramatically different. This reinterpretation does not invalidate the Voyager 2 data. The measurements are still accurate. They still tell us what the system looked like on that particular day. But they force a painful reassessment of how much weight we placed on a single snapshot taken during what now appears to have been an anomalous event. For 4 decades, textbooks described Uranus's magnetosphere using Voyager 2 observations as ground truth. Now we know that ground truth may represent an extreme outlier, the 4% case, rather than the 96% norm. The consequences extend beyond academic debate. Every model of Uranus's magnetosphere that was calibrated against Voyager 2 data may need revision. Every conclusion drawn about moon geology based on the absence of water ions may need reconsideration. Every estimate of radiation belt intensity used to plan future missions may need adjustment. The single data point we built our understanding on turned out to be the wrong data point. Not wrong in the sense of erroneous, but wrong in the sense of unrepresentative. This is the broader lesson Uranus teaches about planetary science. A single flyby, no matter how sophisticated the spacecraft, captures one moment in time. For a planet whose magnetosphere reconfigures itself every 17 hours, whose seasons last 42 years, whose thermosphere has been cooling for decades, and whose magnetic geometry creates conditions unlike anything else in the solar system, one moment is nowhere near enough. The magnetic field of Uranus is not just tilted and offset. It is the engine of a system-wide strangeness that connects the deep interior to the outermost reaches of the magnetosphere, that drives auroral patterns visible only to the most sensitive infrared instruments ever built, that creates a space environment so variable that the only close-up measurement we have may represent a rare extreme, and that produces an upper atmospheric cooling trend whose cause remains genuinely unknown after years of study by multiple research teams using multiple observatories. And yet the magnetic field, for all its strangeness, is only the visible expression of processes occurring deep inside the planet. The field is generated somewhere within Uranus's interior, in a layer of compressed, electrically conducting fluid whose composition, depth, and dynamics we can only infer from external measurements. The shell dynamo that produces the offset, tilted field must be telling us something about the internal structure, about how materials are layered, how heat moves or fails to move, and why Uranus differs so profoundly from its near-twin Neptune in ways that no single explanation has yet resolved. The magnetic field points inward, toward an interior that holds the next set of puzzles. For decades, the deepest of those puzzles was a missing energy budget, a giant planet that appeared to have lost its internal warmth entirely. That mystery, too, has recently begun to crack open, and what lies inside is stranger than the silence it replaced. For decades after Voyager 2, one number haunted every discussion of Uranus. That number was effectively zero. It was the measured difference between the thermal energy Uranus radiated into space and the solar energy it absorbed. On every other giant planet, this difference is significant. Jupiter radiates roughly 67% more energy than it receives from the Sun. Saturn radiates about 78% more. Even Neptune, a near twin of Uranus in size and composition, radiates approximately 2.6 times more energy than it absorbs. These excesses represent internal heat, primordial warmth left over from formation, gravitational energy released by ongoing contraction, or both. Giant planets are supposed to glow from within. They are cooling engines, slowly shedding the thermal energy stored during the violent collapse of gas and ice that built them billions of years ago. Uranus appeared to break this rule entirely. Voyager 2's infrared measurements, combined with estimates of how much sunlight the planet absorbs, suggested that the thermal output and solar input were nearly in balance. The internal heat contribution appeared negligible, so small it could not be distinguished from measurement uncertainty. Among the 4 giant planets, Uranus alone seemed thermally dead, as if whatever furnace had once burned inside it had been extinguished or sealed off so completely that no detectable warmth escaped. This result was deeply unsettling. Formation models predicted that Uranus should still be losing significant heat. A planet 14.5 times the mass of Earth, assembled from the gravitational collapse of gas and ice, roughly 4.5 billion years ago, should not have cooled to equilibrium this quickly. The thermal timescales did not work. Even with generous assumptions about cooling efficiency, Uranus should still be releasing measurable internal energy. Its apparent silence suggested either that something about the planet's interior trapped heat far more effectively than any standard model predicted, or that the measurements were wrong. The measurements turned out to be incomplete. In July of 2025, a team led by Xinyue Wang and Liming Li at the University of Houston published a study that rewrote the energy budget of Uranus. Instead of relying on the snapshot captured by Voyager 2, the team assembled a global average radiant energy budget spanning an entire Uranian orbital period from 1946 to 2030, using decades of spacecraft observations, ground-based data, and atmospheric models. The key insight was that Uranus's 84-year orbit produces enormous seasonal variations, in how much solar energy the planet absorbs. The extreme axial tilt means the sunlit pole receives far more concentrated radiation during solstice than the equator receives during equinox. These variations are so large, the absorbed solar power can swing by more than 85% between hemispheric extremes, that any single measurement taken at one point in the orbit risks capturing a seasonal fluctuation rather than the long-term average. When the team accounted for these seasonal variations and computed the average over a full orbit, the result was clear. Uranus's emitted thermal power consistently exceeded its absorbed solar power. The planet is losing energy. It does have internal heat. The measured internal heat flux came out to approximately 0.078 watts per square meter, with an uncertainty of plus or minus 0.018. In practical terms, Uranus emits roughly 12.5% more energy than it absorbs from the Sun. This is a modest number. Jupiter's internal heat flux is many times larger. Neptune's is approximately 5 times greater at roughly 0.4 watts per square meter. But it is not zero. The long-standing claim that Uranus has no internal heat turned out to be an artifact of measurement limitations, a conclusion drawn from a single flyby snapshot that caught the planet at one point in its orbital cycle and lacked the temporal baseline to separate seasonal effects from the BROS underlying thermal signal. The resolution of the missing heat mystery raised an immediate follow-up question. Why is Uranus's internal heat so much weaker than Neptune's? The two planets are strikingly similar in many respects. Their masses differ by only about 15%. Their radii differ by only a few percent. Both have hydrogen-helium atmospheres enriched with methane. Both have similar effective temperatures. Both have oddly tilted magnetic fields, though Neptune's tilt is less extreme. If they formed from similar materials through similar processes, their internal heat outputs should be comparable. Instead, Uranus produces roughly 1/5 the heat flux that Neptune does. The most frequently cited explanation circles back to the giant impact. If a massive collision knocked Uranus onto its side early in its history, the energy of that impact could have mixed the planet's interior far more thoroughly than would otherwise occur. On an undisturbed giant planet, the interior settles into a layered structure, a dense core surrounded by progressively lighter materials, with clear compositional boundaries between layers. These boundaries can act as insulating barriers, trapping heat in the deep interior and allowing it to escape only slowly over billions of years. The slow escape is what produces the sustained internal heat flux we observe on Jupiter, Saturn, and Neptune. A sufficiently violent impact could disrupt this layered structure, mixing materials across compositional boundaries and eliminating the insulating barriers. With no barriers to trap it, the primordial heat would escape much more rapidly, perhaps within the first billion years after the collision. By the time we observe Uranus today, 4.5 billion years later, most of the internal heat would already have radiated away, leaving only the small residual flux that Wang and Li measured. This explanation is plausible but difficult to test. We do not know what Uranus's interior actually looks like. We have never directly measured its internal structure. Everything we infer about the layers inside the planet comes from external observations: the gravitational field, the magnetic field, the atmospheric composition, and now the thermal output filtered through theoretical models that contain significant uncertainties. Different models produce different internal structures, and the data we have cannot distinguish between them definitively. A study published in the journal Astronomy and Astrophysics in December of 2025 by Luca Morf and Ravit Held at the University of Zurich pushed this uncertainty even further. Their work explored a wider range of possible interior models for Uranus and Neptune than previous studies had considered. The standard assumption that these planets are dominated by water, ammonia, and methane ices beneath their hydrogen-helium envelopes gives them the name ice giants. But Morf and Held showed that interior models dominated by rock rather than ice can also reproduce the observed gravitational fields and other external measurements. Uranus and Neptune might not be ice giants at all. They might be rock giants, planets with rocky interiors surrounded by relatively thin layers of ice and gas. If the interior is rockier than assumed, the thermal evolution changes. Rock conducts and retains heat differently from ice. The compositional gradients that trap or release internal heat would have different depths and different insulating properties. The impact hypothesis, which depends on disrupting ice-dominated layers, would need revision. Even the shell dynamo that generates the magnetic field would operate in a different medium, potentially explaining some of the differences between the magnetic fields of Uranus and Neptune. The honest summary is this: Uranus does have internal heat, resolving a decades-old mystery, but that internal heat is anomalously weak compared to Neptune's, and we do not know why. The leading explanation involves a giant impact that mixed the interior and accelerated heat loss, but the interior itself remains almost completely unconstrained by direct observation. We are inferring the structure of a planet's deep interior from measurements made 3 billion kilometers away, and the range of structures consistent with the data is wider than most people realize. Above the mysterious interior, the atmosphere of Uranus presents its own set of contradictions. In visible light, the planet looks like the quietest world in the outer solar system, a pale sphere of blue-green haze with almost no discernible features. This visual blandness led to years of dismissal. Compared to Jupiter's turbulent bands and Great Red Spot, compared to Saturn's elaborate ring system and hexagonal polar vortex, compared even to Neptune's dark spots and supersonic winds, Uranus seemed featureless, boring, a planet where nothing happened. Infrared and radio observations told a completely different story. Beneath the bland visible surface, Uranus harbors wind speeds exceeding 900 kilometers per hour at certain latitudes. These winds are not gentle breezes, they are powerful flows that rank among the fastest in the solar system, exceeded decisively only by Neptune, which holds the record with winds more than twice as fast. The wind pattern on Uranus is dominated by strong retrograde flow near the equator winds, blowing against the direction of the planet's rotation, and prograde jets at higher latitudes. This overall structure resembles the banded wind patterns on Jupiter and Saturn, but the details differ in ways that atmospheric models struggle to reproduce. Cloud features do appear when you look closely enough and in the right wavelengths. Starting in the late 1990s, as Uranus approached its 2007 equinox, ground-based telescopes with adaptive optics and the Hubble Space Telescope began detecting bright cloud features at mid-latitudes. Some of these clouds were enormous, thousands of kilometers across and remarkably bright in near-infrared images, punching through the upper methane haze layer like white peaks emerging above a fog bank. Their appearance suggested vigorous convective activity in the deeper atmosphere, with plumes of material rising from below and condensing at altitude. The timing was significant. The equinox represented a transition point in Uranus's seasonal cycle, a moment when both hemispheres received roughly equal solar illumination after decades of extreme polar heating. Atmospheric models predicted that this transition should trigger changes in circulation patterns, potentially stirring up cloud activity that had been suppressed during the long solstice. The observations seemed to confirm this prediction. Uranus was waking up, but the cloud activity did not follow the seasonal script cleanly. Some storms appeared in the hemisphere that was moving into darkness rather than the one emerging into light. Others intensified years after the equinox, well past the point where the seasonal forcing should have been strongest. A particularly violent storm system appeared in 2014, producing features bright enough to be detected by amateur astronomers with backyard telescopes, a remarkable achievement for a planet 3 billion kilometers away. The storm's location and timing did not match any seasonal model. The atmosphere of Uranus appears to respond to seasonal changes, but with lags, asymmetries, and surprises that suggest the atmospheric dynamics are more complex than solar forcing alone can explain. Internal heat, however weak, may play a role in driving convection. The composition of the deep atmosphere, which likely includes hydrogen sulfide, water, and ammonia, in addition to the methane and hydrogen visible at the top, may create layered structures that influence how and when convective storms break through to observable altitudes. The vertical distribution of haze particles, which gives Uranus its characteristic pale color, may vary with season in ways we have not yet tracked through a full orbital cycle. The mention of hydrogen sulfide is not incidental. In 2018, a team using the Gemini North Telescope in Hawaii confirmed that the uppermost cloud deck of Uranus contains hydrogen sulfide ice, a finding that had been suspected but never directly measured. The detection came from near-infrared spectroscopy that identified the spectral signature of hydrogen sulfide just above the main cloud layer. This is a genuinely important distinction. On Jupiter and Saturn, the corresponding cloud layer is composed of ammonia ice. The fact that Uranus's clouds are dominated by hydrogen sulfide rather than ammonia tells us something about the deeper atmospheric chemistry. Ammonia has been locked away at lower altitudes, possibly dissolved in a deep water layer or bound up in ammonium hydrosulfide compounds well below the visible cloud deck. The overall sulfur-to-nitrogen ratio in Uranus's atmosphere differs from that of the gas giants, reflecting either different formation conditions or different internal processing of primordial materials. If you could somehow stand in the upper cloud deck of Uranus, setting aside the impossibility of standing in an atmosphere with no solid surface, the experience would be profoundly alien. The clouds around you would smell of rotten eggs, the signature odor of hydrogen sulfide. The temperature would hover around -200 degrees Celsius. The sky above would be a pale blue-green haze, dimly lit by a sun so distant it would appear as little more than a bright star. Winds would tear past at hundreds of kilometers per hour, and beneath your feet, the atmosphere would simply continue downward, growing denser and hotter with depth, transitioning from gas to supercritical fluid to the exotic compressed states, where superionic water carries the currents that generate the planet's magnetic field. There is no ground to reach. Uranus's atmosphere all the way down, a world with no surface, no coastline, no bedrock, just an ever-thickening ocean of gas that gradually becomes something no longer recognizable as gas at all. The methane that gives Uranus its color also drives a complex photochemistry in the upper atmosphere. Ultraviolet sunlight breaks methane molecules apart, producing fragments that recombine into heavier hydrocarbons, ethane, acetylene, diacetylene, and more complex organic compounds. These photochemical products form the haze particles that blanket the upper atmosphere and give Uranus its characteristically washed-out appearance. The haze is thicker and more uniform than Neptune's, which is one reason Uranus looks paler despite having a similar bulk composition. Why the haze layer differs between the two planets is not fully understood, but it likely relates to differences in vertical mixing rates, how efficiently the atmosphere stirs material from the deep interior up into the photochemical zone, which in turn connects to the internal heat budget. A planet with stronger internal convection, like Neptune, would churn more methane upward, fueling more photochemistry but also punching more holes in the haze layer, creating the darker, more vivid blue that Neptune displays. Uranus, with its weaker internal heat, may be a more sluggish mixer, producing a more uniform and optically thick haze. This connects to another unresolved problem that planetary scientists call the energy crisis. Even after the thermosphere has cooled from 750 Kelvin to around 450 Kelvin over the past 3 decades, that temperature is still far higher than sunlight alone can explain at 19 astronomical units from the Sun. Solar ultraviolet radiation deposits energy in the upper atmosphere, but the amount is insufficient to maintain temperatures above a few hundred Kelvin. Something else is heating the thermosphere-magnetospheric coupling, gravity wave dissipation breaking upward from the deeper atmosphere, or some combination, and the balance between this mysterious heating and the long-term cooling trend defines the thermal state of the upper atmosphere at any given time. The energy crisis is not unique to Uranus. Jupiter and Saturn also have thermospheres hotter than solar heating predicts. But Uranus's version of the problem is complicated by the extreme magnetic geometry, the unusual seasonal forcing, and the fact that the cooling trend itself has no confirmed explanation. Nobody has ever watched Uranus through even half of its 84-year orbit with modern instruments. The earliest high-quality observations date to the 1980s. We have covered barely 40 years, less than half a Uranian year. We are trying to understand a planet's climate from less than one complete seasonal cycle of data, and the cycle itself is longer than the entire history of space-based astronomy. Surrounding this enigmatic atmosphere is a ring system that adds yet another dimension of strangeness. Uranus has 13 known rings, and they look nothing like Saturn's. The rings were not discovered by a telescope pointed at the planet. They were found by accident in 1977, when astronomers watched a distant star pass behind Uranus during a stellar occultation. They expected the starlight to vanish once, when the planet's disk blocked it. Instead, the light dimmed 5 times before the planet intervened, and 5 times again afterward, in a symmetric pattern that could only mean one thing. Narrow rings of material encircled the planet, each one briefly blocking the starlight as it passed through the line of sight. 9 rings were confirmed that night. 4 more were identified later. Saturn's rings are broad, bright, and primarily composed of water ice particles ranging from tiny grains to house-sized boulders. They reflect sunlight brilliantly and are visible through even modest telescopes. Uranus's rings are narrow, dark, and composed of particles that reflect very little light. Most of the rings are only a few kilometers wide, separated by vast empty gaps. The particles appear to be coated with or composed of dark, carbon-rich material, rather than clean ice. The overall reflectivity of the Uranian rings is comparable to charcoal. The narrowness of the rings is itself a puzzle. Ring dynamics theory predicts that narrow rings should spread over time due to collisions between particles. Without some confining mechanism, a narrow ring should gradually smear itself into a broader, more diffuse structure. Saturn's rings are broad partly because they have had billions of years to spread. Uranus's rings remain narrow, which suggests that something is actively confining them. The most likely candidates are shepherd moons, small satellites orbiting on either side of a ring, whose gravitational influence herds the ring particles into a tight band. Voyager 2 discovered several shepherd moons during its flyby, and their positions match the edges of specific rings. But not every ring has an identified shepherd pair, and the dynamics of the confinement mechanism are not fully understood for the Uranian system. The epsilon ring is the most prominent and the strangest of the 13. It is the widest, the most reflective though that is a relative term, since even the epsilon ring reflects very little sunlight and the most eccentric. Its width varies dramatically as it traces its elliptical orbit, narrowing to roughly 20 kilometers at its closest approach to Uranus, and broadening to approximately 96 kilometers at its most distant point. This variation is actively maintained by the gravitational influence of 2 small shepherd moons, Cordelia, orbiting just inside the ring, and Ophelia, orbiting just outside. The gravitational interplay between these 2 moons and the ring particles creates a dynamic equilibrium that prevents the ring from spreading or collapsing. Remove either shepherd and the epsilon ring would dissipate within a geologically brief span of time. The ring exists because the moons exist, and understanding why those moons occupy their particular orbits connects to the broader question of how the entire ring-moon system formed and evolved. The picture grew more complex between 2003 and 2005, when the Hubble Space Telescope discovered 2 faint outer rings far beyond the main system. Designated Mu and Nu, these rings orbit at roughly twice the distance of the epsilon ring and are composed of an entirely different population of material. While the inner rings consist of relatively large, dark particles, boulder-sized chunks of carbon-rich material, the outer rings are made of micrometer-sized dust grains, more similar to the faint rings of Jupiter than to anything else in the Uranian system. The dust particles in these outer rings are continuously produced by collisions among small moonlets embedded within the rings, and are gradually lost to radiation pressure and drag, meaning the rings must be constantly replenished. They are not ancient structures passively orbiting. They are active systems maintained by ongoing destruction and creation at the micrometer scale. During the 2007 equinox, when the ring system was viewed nearly edge-on from Earth, astronomers detected additional fine dust structures threading through the gaps between the narrow main rings. These tenuous dust sheets are invisible when the rings are viewed face-on because the reflected light from the dust is overwhelmed by the planet's glare. The edge-on geometry reduced the planet's apparent brightness and allowed the faint dust to stand out, revealing that the spaces between the main rings are not truly empty, but contain a diffuse population of tiny particles whose origin and dynamics are not yet understood. The rings also orbit in the planet's equatorial plane, which means they share the 98-degree tilt. When viewed from Earth, the ring system appears nearly face-on during solstice and edge-on during equinox. This changing geometry affects how easily the rings can be observed and studied, and it means that decades can pass between optimal viewing windows for different ring features. The moons of Uranus complete the picture of a planetary system that seems assembled from mismatched components. 29 known moons orbit the planet, ranging from tiny irregular objects a few kilometers across to Titania, the largest, at approximately 1,580 kilometers in diameter. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are all substantial worlds with distinct surface features, and every one of them presents unresolved questions. Miranda is the most visually dramatic. Despite being only about 470 kilometers across, small enough that its gravity barely holds it in a spherical shape, Miranda displays one of the most geologically tortured surfaces in the solar system. Voyager. 2 images revealed enormous fault canyons up to 20 kilometers deep, layered terrain called coronae that resemble nothing seen on any other moon, and abrupt boundaries between ancient cratered plains and younger grooved terrain. The surface looks as if the moon was shattered and reassembled, or as if internal geological processes far more vigorous than a body this small should produce once reshaped entire hemispheres. The most visually arresting feature on Miranda is Verona Rupes, a cliff face that drops roughly 20 kilometers from rim to base. To put that in perspective, the Grand Canyon averages about 1.5 kilometers in depth. Verona Rupes is more than 13 times deeper, carved into a moon so small that its entire diameter is less than the distance from Los Angeles to San Francisco. The cliff is not a simple vertical wall. It slopes steeply, and the precise geometry remains uncertain because Voyager 2 imaged it at an oblique angle during a brief flyby. But even the most conservative estimates make it the tallest known cliff face in the solar system, an almost absurd geological feature on a world where the surface gravity is so weak, less than 1% of Earth's, that an object falling from the top would take nearly 12 minutes to reach the bottom. It would land gently, relatively speaking, at a terminal velocity far lower than what the same fall would produce on Earth. The cliff exists not because of violent forces currently acting on Miranda, but because the weak gravity that makes such a feature possible also prevents erosion from wearing it down. There is no wind, no rain, no plate tectonics to degrade the scarp. It simply endures, a frozen testament to whatever forces created it. The 3 large coronae, Arden, Elsinore, and Inverness, are equally difficult to explain. These are roughly ovoid regions of ridged and grooved terrain, bounded by sharp tectonic scarps that look completely different from the ancient cratered plains surrounding them. Inverness Corona, the most prominent, displays a striking pattern of concentric ridges resembling a chevron or a racetrack, nestled into the landscape as if stamped there by some enormous geological press. The boundaries between the coronae and the older terrain are abrupt, with almost no transitional zone. One type of surface simply stops and another begins, suggesting that whatever process created the coronae operated within well-defined limits, rather than gradually reworking the entire surface. The tidal heating hypothesis explains these features more naturally than the catastrophic disruption model. If Miranda once occupied an orbital resonance, a configuration where its orbital period formed a simple ratio with that of another moon, such as 3:1 with Ariel, the periodic gravitational flexing would have heated its interior non-uniformly. Rock and ice near the surface would have experienced the greatest tidal stress at specific latitudes and longitudes, creating localized zones of enhanced heating. These zones could have driven diaporism, the buoyant upwelling of warmer, less dense material through a cooler, denser crust, producing the coronae as surface expressions of rising plumes from below. When the orbital resonance eventually broke, probably because tidal dissipation within Miranda itself altered its orbit enough to push it out of the resonant configuration, the heating stopped and the geological activity froze in place. This model is attractive because it explains not just Miranda but potentially other features in the Uranian system. Orbital resonances can migrate through a moon system over time as tidal interactions evolve the orbits. A resonance that heated Miranda in the past might have previously heated Ariel, or might in the future sweep through the orbit of another moon. The geological evidence on Ariel, its resurfaced plains and extensive fault systems, is consistent with a period of past tidal heating, possibly driven by a resonance that later migrated to Miranda's orbit. Ariel shows evidence of relatively recent geological resurfacing. Its surface has fewer large impact craters than Umbriel or Oberon, suggesting that some process erased older craters, most likely cryovolcanism, the eruption of water-ammonia mixtures or other volatile fluids onto the surface. Aerial surface displays extensive fault systems and smooth plains that may represent frozen lava flows, not of molten rock, but of liquid that was warm enough to flow across the surface before freezing in the extreme cold. Whether Ariel is still geologically active or whether this resurfacing ended long ago is unknown. Titania and Oberon are larger and more heavily cratered, their surfaces recording billions of years of impact history. Both show evidence of past geological activity fault systems on Titania, dark material on crater floors on Oberon that may represent cryovolcanic deposits, but the extent and timing of this activity remain uncertain. Umbriel is the darkest of the 5 major moons, its surface uniformly coated with material so dark it reflects only about 21% of incoming light. A single bright feature, a ring of bright material on the floor of a large crater, stands out against the otherwise featureless darkness. What produced this bright annulus and why the rest of Umbriel is so uniformly dark are open questions. Beyond the geological puzzles of individual moons, there is a broader question that an orbiter could address. Do any of the larger Uranian moons harbour subsurface oceans? The possibility is not as remote as it might sound. Titania, the largest Uranian moon, is comparable in size to Saturn's moon Rhea and significantly larger than Enceladus. The Saturnian moon confirmed to have a global subsurface ocean. Its substantial diameter places it in the size range where subsurface liquid becomes theoretically plausible. Oberon, at approximately 1,520 kilometers, is nearly the same size. Theoretical models suggest that both Titania and Oberon could retain liquid water layers beneath their icy crusts, if even modest amounts of antifreeze compounds, ammonia dissolved in water, for instance, are present in their interiors. Ammonia depresses the freezing point of water by tens of degrees, allowing liquid to persist at temperatures well below the normal freezing point. The heat required to maintain these liquid layers could come from residual radioactive decay in the moon's rocky cores. Unlike tidal heating, which depends on orbital configuration and can switch on and off as resonances evolve, radiogenic heating is steady and predictable. Any rocky body of sufficient size produces heat from the decay of long-lived radioactive isotopes, potassium, thorium, uranium, for billions of years. For Titania and Oberon, the question is whether this radiogenic heat, combined with whatever insulation the icy crust provides, is sufficient to prevent their interiors from freezing solid over 4.5 billion years. Models suggest it may be, particularly if their interiors are differentiated, meaning the rock has settled to the center and the ice sits on top, creating a natural insulating blanket. Ariel, smaller but geologically more active in its past, presents a similar case. Its resurfaced terrain suggests that liquid or semi-liquid material once reached the surface, which requires a heat source capable of melting interior ice. If that heat source persists at low levels today, a thin liquid layer could survive beneath the crust. Detecting these oceans from orbit would use the same techniques that revealed subsurface water on Europa and Enceladus. An orbiting magnetometer could detect induced magnetic fields generated by a conducting liquid layer responding to the time-varying magnetic environment of Uranus. And given how dramatically that magnetic environment varies with every single rotation of the planet, the inducing signal at Uranus would actually be stronger and more diagnostically useful than the signals used at Jupiter and Saturn. And then, in August of 2025, the James Webb Space Telescope added a 29th moon to the list. A team led by Mariame El-Mutamid at the Southwest Research Institute identified a tiny object in a series of 10 40-minute exposures taken by Webb's near-infrared camera on February 2, 2025, designated S 2025 U1. The moon is estimated to be only 8 to 10 kilometers across, roughly the size of a small city orbiting between the moons Ophelia and Bianca at a distance of approximately 57,800 kilometers from the planet's center. It is the smallest and faintest Uranian moon ever detected, so dim that Voyager 2 flew right past it without noticing, and every telescope before Webb lacked the sensitivity to pick it out from the glare of the rings and the planet itself. The discovery underscored two things simultaneously. First, the Uranian system is more populated and more complex than our current census reveals. If Webb found a moon this small with a single set of exposures, there are almost certainly more waiting to be discovered. smaller objects, fainter objects, objects orbiting at distances or inclinations that have not yet been surveyed. Second, our most detailed reconnaissance of the system. The Voyager 2 flyby missed it entirely. Voyager 2 discovered 10 moons during its encounter, a remarkable achievement. But it spent only hours in the system, and its cameras, while state-of-the-art for 1986, lacked the infrared sensitivity and exposure depth that Webb brings to bear from 1 billion kilometers farther away. This is the fundamental limitation that runs through every aspect of Uranus science. Every measurement we have, the magnetic field geometry, the atmospheric temperature profiles, the ring structure, the moon surfaces, the radiation environment, the internal heat budget derives from one of 3 sources: a 6-hour flyby conducted 4 decades ago under what now appear to have been anomalous conditions, a distant telescope observations that resolve the planet as a disk only a few arc-seconds across, or theoretical models calibrated against these incomplete observations. Voyager 2 gave us the skeleton. Hubble, Spitzer, Webb, and ground-based observatories have added muscle and skin, but the organism is still largely imagined. We have never orbited Uranus. We have never dropped a probe into its atmosphere. We have never measured its gravitational field with the precision needed to distinguish between competing interior models. We have never sampled the composition of its clouds directly. We have never flown through its magnetosphere long enough to observe its behavior over a full rotation, let alone a full season. We have never mapped the surfaces of its major moons at resolution sufficient to determine whether any of them harbour subsurface oceans. Everything we know about Uranus is drawn from the thinnest possible observational record of any major planet in the solar system. Mercury has been orbited by MESSENGER and mapped in extraordinary detail. Venus has been visited by dozens of missions. Mars has rovers on its surface right now. Jupiter has been orbited by Galileo and Juno. Saturn was orbited by Cassini for 13 years. Even distant Neptune received the same Voyager 2 treatment. That Uranus did a single flyby, but Neptune at least behaved normally during its encounter, giving scientists a representative snapshot of its system under typical conditions. Uranus alone combines minimal observation with maximal strangeness. It is the planet we understand least, and the planet that deviates most from every pattern established by its neighbours. That combination is not a coincidence. The strangeness is partly real Uranus, genuinely differs from the other giants in fundamental ways, and partly an artifact of ignorance. We do not know enough to separate the two. Features that seem anomalous today might turn out to be normal for ice giants once we study one up close. Features that seem normal might turn out to hide deeper mysteries visible only from orbit. The planet demands a dedicated mission, and that mission has been endorsed at the highest levels of planetary science. But translating scientific priority into hardware in space is a process that moves on its own timeline, governed by budgets, politics, and the merciless mathematics of orbital mechanics. The window for reaching Uranus efficiently is not open forever, and every year of delay pushes the arrival date further into the future. The stakes of that delay, and the broader significance of what a mission would reveal, extend far beyond Uranus itself. They reach across the galaxy, to a class of planets we are only beginning to recognize as the most common worlds in existence. In 2022, the United States National Academies of Sciences released a document that would shape planetary exploration for the next decade. The Origins, Worlds, and Life, Planetary Science and Astrobiology Decadal Survey, the result of years of deliberation by more than 130 contributing scientists, ranked its priorities for where NASA should send its next flagship mission. The answer, for the first time in the history of these surveys, was Uranus. A Uranus orbiter and probe was designated the highest priority new flagship mission for the decade. Not Mars, not Europa, which already had a mission in development, not Venus, which had gathered strong advocacy, not a return to Saturn or a first visit to one of the ocean worlds of the outer solar system. Uranus, the planet that most of the public thinks of as the punchline to a joke, the world that has received less spacecraft attention than any other major planet, the giant that looks so boring in Voyager 2's photographs that it was largely ignored for a generation. The scientific community looked at all the options and concluded that Uranus was the place where the greatest unanswered questions lived. The logic behind the decision was layered. At the most immediate level, Uranus represents a class of planet, the ice giant, that we have never studied from orbit. The history of planetary exploration has taught one lesson above all others. Orbiting a planet reveals orders of magnitude more information than passing by it. The breakthroughs that redefined our understanding of the gas giants, the geysers of Enceladus, the methane lakes of Titan, the seasonal evolution of Saturn's polar vortex, the intricate dynamics of ring systems all required years of sustained close-range observation. None of them could have been captured in a single flyby. None of them were predicted before the orbiters arrived. Uranus has never had that sustained observation. Everything we know comes from a single brief flyby and 4 decades of increasingly capable but fundamentally limited telescope observations from billions of kilometers away. An orbiter would change this entirely. It would circle the planet for years, mapping the gravitational field with precision sufficient to constrain interior models, measuring the magnetic field from multiple angles and distances to characterize the dynamo, monitoring atmospheric features through seasonal changes, observing the rings at resolutions Voyager 2 could not approach, and flying past the major moons closely enough to determine whether any of them harbor subsurface oceans. The probe component adds another dimension. Dropped into the atmosphere, a descent probe would directly sample the gases beneath the cloud tops for the first time. It would measure the ratios of hydrogen, helium, methane, ammonia, hydrogen sulfide, and heavier elements at depths no telescope can reach. These compositional measurements would reveal how Uranus formed, whether it assembled from materials similar to those that built Jupiter and Saturn, or from a fundamentally different mix of ices and rocks. The elemental ratios would also test whether the planet is truly an ice giant, as decades of assumption have held, or whether its interior is rockier than expected, as the Morphen-held models from 2025 suggest. The mission concept envisions a spacecraft launched on a heavy-lift rocket, traveling to Uranus on a trajectory that uses a Jupiter gravity assist to shorten the transit time. The optimal launch window for this trajectory falls in the early 2030s. A launch in 2031 or 2032 would allow the spacecraft to swing past Jupiter and reach Uranus after approximately 13 years of flight, arriving in the mid-2040s. Upon arrival, the orbiter would enter orbit around Uranus and begin a multi-year tour. At a designated point, it would release the atmospheric probe on a trajectory that sends it plunging into the atmosphere, transmitting data back to the orbiter during its descent. That timeline is already under pressure. The Decadal Survey was published in 2022. The expectation was that NASA would begin funding mission studies promptly, soliciting a core science team by 2026 and beginning serious engineering development by 2027. Instead, budget constraints have slowed the process. NASA's fiscal year 2025 budget request did not include substantial funding for the mission, and the Outer Planets Assessment Group, an advisory body representing the planetary science community, has repeatedly urged NASA to maintain the timeline as closely as possible. The core science team solicitation has been discussed for 2026, with planning activities potentially starting in 2027, but every year of delay threatens the Jupiter gravity assist window. If that window is missed, the consequences are significant. Without a Jupiter assist, the spacecraft would need to take a longer, less efficient route, potentially adding years to the transit time and increasing mission cost. Alternative trajectories exist. Solar electric propulsion, for instance, can deliver sufficient mass to Uranus orbit with flight times of 12 to 14 years, using repeatable launch windows that do not depend on Jupiter's position. Preliminary analyses have even explored a trajectory using a Starship-class launch vehicle, which could potentially deliver the spacecraft to Uranus within as few as 10 years on a direct trajectory, without any planetary gravity assist at all. But these alternatives introduce their own technical challenges and uncertainties. The scientific community's urgency is not purely about trajectory mechanics. It is also about human expertise. Many of the scientists who worked on Voyager 2, the people who designed the instruments, interpreted the data, and built the foundational models of Uranus's magnetosphere and atmosphere, are aging. Their institutional knowledge of ice giant systems is irreplaceable. Starting mission planning now, while this expertise is still available, would ensure continuity between the only spacecraft data we have and the design of the instruments that will collect the next generation of measurements. Waiting too long risks losing that chain of knowledge entirely. A June 2026 paper published in the Planetary Science Journal by Amy Simon and colleagues provided a comprehensive update on mission challenges and concept developments since the decadal survey. The paper addressed trajectory options, instrument requirements, probe design, and the engineering trades involved in delivering a spacecraft to a planet 19 astronomical units from the Sun. It also highlighted the scientific questions that only an orbiter and probe can answer, questions that remain stubbornly out of reach no matter how capable our telescopes become. Among those questions, several stand out. What is the bulk composition of Uranus? We know the atmosphere is dominated by hydrogen and helium, with significant methane enrichment, but we do not know the ratios of heavier elements, carbon, nitrogen, sulfur, oxygen, that would reveal how and where the planet formed. Did it form near its current orbit, or did it form closer to the Sun and migrate outward? The elemental fingerprint locked inside the atmosphere holds the answer, and only a probe descending below the cloud deck can read it. What generates the magnetic field? We know the field is tilted, offset, and generated in a conducting shell rather than at the core. But we do not know what that shell is made of, how deep it sits, or why the dynamo produces such an unusual geometry. An orbiter measuring the magnetic field from many different positions and distances could map the field's higher-order structure, the details beyond the simple dipole, revealing the shape and depth of the dynamo region. Combined with precise gravitational measurements constraining the density profile, this would tell us more about the planet's internal structure than any external observation can. What drives the atmospheric dynamics? We have seen storms, cloud bands, and supersonic winds, but we cannot explain their energy sources. The internal heat is weak. The solar input is modest at 19 astronomical units. Yet the atmosphere generates wind speeds comparable to Neptune's, which receives even less solar energy but has 5 times more internal heat to drive circulation. Something about Uranus's atmospheric engine does not fit standard models, and sustained orbital monitoring through different seasons is the only way to understand it. Are any of the Moon's ocean worlds? The tidal heating hypothesis for Miranda suggests that orbital resonances once generated significant internal warmth in at least some Uranian moons. Ariel's resurfaced terrain hints at past cryovolcanic activity. If tidal heating occurred in the past, it may still be occurring at low levels today, or residual warmth may sustain liquid water beneath icy crusts. Close flybys with magnetometers and gravity instruments could detect the signatures of subsurface oceans-induced magnetic fields from a conducting fluid layer, or gravitational anomalies consistent with a liquid interior, the same techniques that revealed Europa's and Enceladus's oceans. These are not abstract questions. They connect directly to one of the most consequential discoveries in modern astronomy. Ice giant-sized planets are everywhere. Over the past 15 years, exoplanet surveys conducted by the Kepler Space Telescope, the Transiting Exoplanet Survey satellite, ground-based radial velocity programs, and direct imaging campaigns have revealed a startling pattern in the population of planets orbiting other stars. The most common type of planet in the Milky Way is not a rocky world like Earth. It is not a gas giant like Jupiter. It is something in between a planet roughly 2 to 4 times the radius of Earth, with a mass in the range of Uranus and Neptune. These worlds, collectively called sub-Neptunes, appear to be the single most numerous category of confirmed exoplanet. They outnumber both rocky planets and gas giants in the surveys conducted so far. This discovery carries a profound irony. The most common type of planet in the galaxy corresponds to a category that our own solar system contains exactly 2 examples of, and we have never orbited or probed either one. We have studied gas giants up close for decades. We have sent rovers to the surfaces of rocky planets. But the planets that dominate the galactic census remain, in our own backyard, the least explored class of world. Sub-Neptunes are not simply scaled-down versions of Jupiter. Their internal structures, atmospheric compositions, and formation pathways are likely fundamentally different from those of gas giants. They occupy a transitional regime between rocky planets and hydrogen-dominated giants, a regime where the balance between solid material and gaseous envelope determines everything about the planet's character. Understanding where this transition occurs, how it depends on formation conditions, and what it implies for atmospheric retention, magnetic field generation, and surface conditions requires detailed knowledge of real ice giants, not theoretical models, but measured compositions, observed magnetic fields, and directly sampled atmospheres. Uranus and Neptune are the only ice giants we can study up close. They are the ground truth against which every model of sub-Neptune structure and evolution will be tested. Without that ground truth, exoplanet science is building its models on assumptions rather than measurements. The atmospheric composition of a sub-Neptune 500 light-years away cannot be interpreted without understanding the atmospheric composition of Uranus, which is right here, accessible, and has never been directly measured below the cloud tops. The rock giant hypothesis from the Morph and Held study amplifies this point. If Uranus turns out to be rockier than the ice giant label implies, the implications cascade outward to every sub-Neptune in the exoplanet catalogue. Interior models that assume ice-dominated compositions for these worlds would need revision. The thermal evolution, magnetic field generation, and atmospheric retention of sub-Neptunes would all look different if their interiors contain more rock and less ice than currently assumed. A single atmospheric probe measurement at Uranus, a direct determination of the oxygen-to-hydrogen ratio, for instance, could distinguish between rock-dominated and ice-dominated interior models and reshape our understanding of an entire class of planet. This is why the Decadal Survey ranked the Uranus mission so highly. It is not just about one planet. It is about understanding the most common planetary architecture in the galaxy by studying the nearest accessible example. The science return per dollar is extraordinary because the results apply not just to Uranus but to thousands of known exoplanets, and, by extrapolation, to billions more that surveys have not yet detected. And yet, as of mid-2026, no metal has been cut, no instruments have been selected, no spacecraft bus has been contracted. The mission exists as a concept study, a stack of engineering reports, a scientific consensus documented in a survey that the United States government has traditionally treated as binding, but that budget realities can delay. The planetary science community watches the budget process with a mixture of hope and anxiety, knowing that the trajectory mechanics are unforgiving and that the human expertise needed to build on Voyager 2's legacy is a diminishing resource. There is something fitting, in a melancholy way, about Uranus being the planet that tests our commitment to exploration. It has always been the overlooked giant. William Herschel discovered it in 1781, making it the first planet found by telescope rather than by naked eye. But even that discovery was accidental. Herschel initially thought he had found a comet. The planet's true nature took years to confirm. Its name was debated for decades. It was too faint to attract the kind of public fascination that Jupiter and Saturn commanded. It occupied a lonely position in the outer solar system, far enough from the Sun that its orbital period spans most of a human lifetime, close enough that it should have been found centuries earlier if anyone had looked carefully. Voyager 2's visit in 1986 should have changed the equation. Instead, the bland images and the lack of obvious drama, no great red spot, no dramatic ring system visible in the photographs, no volcanic moons, reinforced the perception that Uranus was the boring planet. The scientific community knew better. The magnetic field data alone should have triggered decades of follow-up investigation. The mismatch between the planet's theoretical heat output and its measured thermal emission should have been a five-alarm scientific mystery. The tortured surface of Miranda should have generated the same excitement that Europa's fractured ice shell produced a decade later. But attention flows to the dramatic, and Uranus refused to perform. Its strangeness was subtle, embedded in numbers and field geometries, rather than splashed across photographs. It required patience, careful measurement, and a willingness to sit with uncertainty rather than rushing to tidy conclusions. The planetary science community eventually came around. The Decadal Survey ranking represents a formal acknowledgement that the quiet planet holds the loudest unanswered questions. Whether the funding follows the acknowledgement remains to be seen. What we can say, standing here in 2026 with 4 decades of post-Voyager data and a cascade of recent discoveries reshaping nearly everything we thought we knew, is that Uranus does not fit. It does not fit the pattern established by the gas giants. It does not fit the models built from first principles. It does not fit the expectations set by its near-twin Neptune, which shares its size and composition but differs in internal heat, magnetic field severity, atmospheric activity, and moon system architecture. Uranus occupies a category of 1, a planet that resembles other giants in its broad strokes but deviates from all of them in its details. The axial tilt is the most visible deviation, but it is not the deepest one. The magnetic field tilt and offset reveal an interior structure unlike anything seen elsewhere. The weak internal heat, now confirmed but still anomalously low, suggests an evolutionary history, possibly shaped by a giant impact that diverged from the other giants billions of years ago and never converged back. The atmosphere hides its complexity beneath a mask of haze, revealing storms and winds only when viewed in the right wavelengths at the right times. The rings are dark and narrow where Saturn's are bright and broad. The moons carry geological scars that suggest past violence and possible present-day subsurface activity, but we lack the data to confirm either. And threading through all of it is the Voyager 2 problem, the foundational dataset that shaped 4 decades of understanding and that now appears to have been collected during a rare solar wind event that distorted the very measurements we built our models on. The only close look we have ever taken at this planet caught it in a state that occurs roughly 4% of the time. We drew our portrait of Uranus from a snapshot taken during a storm, and we treated that portrait as definitive for a generation. The recent discoveries have not resolved the mysteries, they have deepened them. The internal heat exists but is too weak. The thermosphere is cooling, but the cause is unknown. The ionosphere has been mapped in 3 dimensions for the first time, revealing auroral structures and energy transport patterns that do not match simple models. A 29th moon has been found hiding in the ring system, too small and too faint for any previous instrument to detect, a reminder that the system contains more than we have catalogued. The interior may be rockier than the ice giant label suggests, which would rewrite not just the story of Uranus, but the story of the most common type of planet in the galaxy. Each new finding peels back a layer and reveals another layer beneath it. The planet does not become simpler as we learn more, it becomes more complex. The questions multiply faster than the answers, and the answers themselves tend to raise new questions that require new observations that our current instruments cannot provide. This is the nature of Uranus. It is a world that rewards attention with deeper mystery. It does not yield its secrets to casual observation or to single encounters. It demands the sustained, patient, close-range investigation that only a dedicated orbiter and probe can provide, the kind of investigation that transformed Jupiter from a banded disk into a complex world with Galileo and Juno, the kind that revealed Saturn's rings to be dynamic and its moons to be alive with Cassini. Uranus has waited 4 decades for that investigation. The planet itself, of course, does not wait. It continues its 84-year crawl around the Sun, rolling on its side, dragging its tilted magnetic field through the solar wind, radiating its faint internal warmth into the cold of the outer solar system. Its storms churn beneath the haze, its moons orbit in their tilted plane, carrying their geological secrets in silence. Its dark rings circle the equator, confined by forces we only partially understand. The planet does not care whether we visit. It will continue being strange regardless. But we should care. Uranus is not strange because of one famous tilt. It is strange because every major system, the seasons, the magnetic field, the magnetosphere, the interior heat, the atmosphere, the rings, the moons, behaves as if the entire planet was knocked out of alignment with the rules that govern the other giants and then left, for 4 billion years, to evolve along a path that nobody predicted and nobody has yet fully traced. The closer we look, the less the planet resembles the simple category it was assigned to. The more data we collect, the more we realize how much of what we thought we knew was built on incomplete evidence, gathered under anomalous conditions. Uranus is the strangest giant in the solar system. It may also be the most important one we have not yet explored. Somewhere in its tilted, offset, quietly cooling interior lies a set of answers that will reshape how we understand not just this one world, but the billions of ice giant-sized worlds scattered across the Milky Way, the most common planets in the galaxy, born from processes we barely comprehend, orbiting stars we are only beginning to survey. There is one final dimension to this story that deserves attention, because it sharpens the stakes of the Uranus-Neptune comparison for every sub-Neptune in the galaxy. Uranus and Neptune are nearly the same size, nearly the same mass, made from broadly similar materials, and orbiting in the same cold outer region of the same solar system. By every crude measure, they should be twins, and yet they are not. Neptune radiates far more internal heat despite its similar size and composition. Neptune's atmosphere is more active, with darker, more vivid colouring and more prominent storm features. Neptune's largest moon, Triton, is a captured Kuiper belt object orbiting retrograde, a completely different kind of moon system from the orderly prograde orbits of Uranus's major satellites. Even their magnetic fields, while both tilted and offset, differ in degree and detail. These differences matter for exoplanet science because they demonstrate that ice giant-sized planets are not a monolithic category. Two worlds that look nearly identical on paper can diverge dramatically in their internal heat, atmospheric behaviour, magnetic structure, and satellite systems. If this kind of diversity exists between two planets that formed in the same system from the same reservoir of material, then the diversity among the billions of ice giant-sized exoplanets in the galaxy must be immense. Sub-Neptunes orbiting different stars, formed from different protoplanetary disks at different distances and different epochs, could display a range of properties far wider than the already significant Uranus-Neptune gap. This realization undercuts any attempt to build a single generic model for sub-Neptune interiors, atmospheres, or magnetic fields. There is no one-size-fits-all ice giant. The category contains multitudes, and the only way to anchor our understanding of that diversity is to study the two examples we have access to, not from a distance, not through a single flyby, but with the sustained close-range observation that only dedicated orbital missions can provide. The Uranus-Neptune dichotomy also poses a specific scientific question that has never been answered. What caused the divergence? Was it the giant impact that knocked Uranus sideways, mixing its interior and draining its primordial heat? Was it a difference in formation location within the protoplanetary disk, giving the two planets slightly different initial compositions? Was it the capture of Triton, which may have disrupted Neptune's original moon system and injected tidal energy into the planet's interior? Or was it something subtler, a difference in migration history, or in the timing of late heavy bombardment, or in some other process that we have not yet considered? Each of these hypotheses makes testable predictions about Uranus's interior composition, heat flow, and satellite system predictions that a Uranus orbiter and probe could evaluate directly. The mission would not just study one planet, it would provide the comparative data needed to understand why two nearly identical worlds ended up so different. And that comparison would echo outward across the exoplanet census, informing how we interpret every sub-Neptune atmosphere spectrum, every ice giant mass radius measurement, and every magnetic field estimate for worlds we will never visit, but are learning to characterize from afar. The answers are there. They have been there for 4.5 billion years, locked inside a pale blue-green sphere rolling silently through the outer dark. All we have to do is go and look.